Hello friends, so today we'll be discussing a problem on abstract algebra, and this is a problem which was asked in GATE. And for previous problems and other problems you can visit this link, and also the previous problem were explained in the video which the link is provided in the description. So let's see the problem. So let Qx be the ring of polynomials over Q, then find the total number of maximal ideals in the quotient ring Qx mod x to the power 4 minus 1. So we are given a polynomial ring and we need to find out the number of maximal ideals in this. Okay. So I recommend you to pause this video and try for a solution. Okay. So I hope you had tried the solution and possibly got the solution. So recall that what is maximal ideal? So if you have R and then I, then this I is called a maximal ideal in R if I is a proper ideal and I is not equals to the trivial ideal, and there does not exist any ideal between I and R. Okay, then this is called maximal ideals. Maximal means it's a maximum. There is no in between I and R. So now this is called maximal ideal, and we need to find out how many maximal ideals are there in this quotient ring. Okay, so the following theorem help you to determine the number of what are the ideals in the quotient ring. So if it is third isomorphism theorem, third isomorphism. Yeah. So it says that if R is a ring and J be an ideal of R, and let I be an ideal of J, then I mod J is an ideal of R mod J. Okay. So what are the all the ideals of R mod J? Is like all the ideals of I mod J. Okay. And we have the following isomorphism theorem. It says that if you take R mod J mod I mod J, because now I know that this is an ideal of this, and hence this quotient makes sense. This quotient is nothing but R mod I. Okay. So what we need to determine is like Qx mod x4 minus 1. So this is my R or R mod J. So what are the ideals of this? So I have to find ideals of x to the power 4 minus 1 and mod out by J. Okay, so these are the ideals of this R mod J ring. Okay, and this is nothing but Qx mod x to the power 4 minus 1. Okay, so we know what are the ideals of the Qx mod x to the power 4 minus 1. So now the problem is how to determine the maximal ideals. Okay, so we know that R mod I is a field if and only if I is a maximal ideal of R. So in order to determine which of the ideal is maximal, so we need to see when this quotient is a field. Okay, and now as Q is a PID, we know that maximal ideals is same as like the ideal generated by irreducible thing. So it means that if the polynomial, so yeah, so we have this as I told earlier. So now I is a maximal ideal if and only if Qx mod I is a field. Okay. Now when is this field? So since this is a PID, therefore we need to consider the ideals of this which are irreducible over Q. Why? Because Q is a PID. Okay. So since Q is a PID, so the ideal generated by irreducible element will be maximum. So what is the goal finally? So find out the irreducible factors of x to the power 4 minus 1 and irreducible in qx, okay, or in q. Okay, so see, we can factor x to the power 4 minus 1 as x square plus 1, x minus 1, and x plus 1. And all these factors are irreducible in q. Okay, this is a linear factor and hence irreducible. This is also a linear and hence irreducible. And this, the roots are plus minus I, which are not in q and hence irreducible. Therefore, ideals of this, which are maximal in this, will be x mod I by x to the power 4 minus 1. Why? Because this is an ideal of this and hence this whole is an ideal of this. Similarly, x plus 1 by x to the power 4 minus 1 and finally x square. So this is this angular bracket. X square plus 1 by x to the power 4 minus 1. So there are three maximal ideals of qx by x to the power 4 minus 1. So the two theorems, I'll just summarize, are important. That what are the ideals of R mod J? So the ideals of R mod J are I mod J, where I is an ideal of J. And we have the isomorphism theorem, which says that this is isomorphic to R mod I. And R mod I is a field if and only if I is maximal. Okay. And in PID, maximal, it's same as prime and which is irreducible. Okay. So thank you for your time and patience. We'll meet again tomorrow. New problem in topology.